Bismillah Rahman Rahim. So today we are here with another lecture for the mechanics of material, and again we would be discussing today the beam problem. So we would draw the shear force and bending moment diagram for this cantilever type beam, and also we have to find the stresses, the normal stresses at point B. So here, as you could see in the figure, we have a beam. One end of the beam is fixed, whereas the other end of the beam is free. So this is a cantilever beam. And you could see the loading. Here we have uniformly distributed load, UDL, and the intensity of this UDL is 3 kips per feet, that is 3 kilopounds per foot. And the span over which this UDL is acting, it is 8 feet. And then at point D, we have a L section which is connected to the main beam. And on this L section, you could see a concentrated load or point load, which is 10 kips. The dimensions of the beam is given 8 feet, 3 feet between point C and D, and 2 feet between point D and point E, and 3 feet between point E and point D. Let's read the statement of the problem. The structure shown is constructed of a W10 into 112 rolled steel beam. So this is actually the coding for the beam. It is made of rolled steel. This is the material, rolled steel. So the beam is made of rolled steel, and its coding is W10 by 112. Part A, draw the shear force and bending moment diagrams for the beam for the given loading. And part B, determine normal stress in sections just to the right and left of point B. So for this beam, we have to draw the shear force and bending moment diagram, and also we have to find the stress, the bending stresses in this beam just at the right side of the point D, or at the end at the left side of point B. So how to solve this problem? As we discussed before in the last lecture, that how to draw the shear force and bending moment diagrams. So we would be using the same steps. So solution steps. Number 1, replace the 10 kips force at point E by equivalent force couple at point B. So first we have to simplify the problem. Here we could see that here we have an L section which is connected at point B, and the loading is at point E. So what we have to do, we have to simplify our problem. So we have to shift this load from point E to point B. So we have to replace this load by a force couple system at point D. How to do it? We would see in the coming slides. Step 2 for the solution, find the reaction force and reaction moment of the support. So here you see this is the support which is actually holding the beam. For this support, from the support, how much reaction force is coming, how much reaction moment is coming, which is actually keeping the beam intact in this position. So we have to find that. And third, find the internal shear force and bending moment throughout the beam. That is, we have to draw the shear force and bending moment diagram. So we have to use the section method. We have to take a number of sections, and we have to develop an equation for the, we have to develop the general equation for the shear force and bending moment for each section. And then by utilizing those equations, we have to determine the values, we have to compute the values of shear force and bending moment throughout the beam, and afterward we have to use those values to draw the shear force and bending moment diagram. And at the end, we have to use the beam flexural formula to determine the normal stresses in the beam, that is at point D, at the left hand side of the point D and right hand side of the point D. So starting the problem with the first solution step, which is we have to replace the 10 kips force at E by the equivalent force couple at point B. So here this is the 10 kips load. We have to shift this to point D so that we could eliminate this section, and we simplify the problem. So what we have to do? We have to shift this load here at point D. But when the load is here, the load is on the beam at the same time it is producing a moment, because this is the moment arm. It is producing a moment at point D. So when you are replacing this load, or when you are shifting this load from point E to point D, so we have to also accompany this load with the couple. And when the load is here, you could see that it is producing a clockwise moment. So it is producing a clockwise moment. So the load itself is 10 kips, and the moment which is associated with this load, it is 10 times 10 multiplied by the moment arm. And how much is this moment arm? You could see that this moment arm is 2. So 10 into 2 is 20. So 20 kip foot is the couple associated, or the moment associated with this load. So now we have shifted the load which was acting at point E, 10 kips load which was acting at point E to point D. So now we have simplified the problem. You could ignore this section, the L section of the beam from your main beam. So next, second step, find the reaction force and reaction moment of the support. So as you could see that the UDL is acting in the downward direction, and also this load is acting in the downward direction. So easily we could assume that the reaction force coming from the support would be in the upward direction. And let's say this is RB. At this moment, we don't know what is its value. We have to find its value. Secondly, if you see that this load is acting here, it is producing a counterclockwise moment, and also this load is acting here, and at this point, at point B, it is producing a counterclockwise moment. So the support reaction moment is more probably clockwise. It would be clockwise. So MB would be clockwise. So MB clockwise. Next, we have to find out its value. So in order to find out the value for RB, we have to use the first condition of equilibrium, that is summation of all of the vertical forces must be equal to 0. And for this, I am taking the upward forces as positive and the downward forces as negative. So the intensity of UDL is 3, and it is acting the length of 8 feet. So the resultant of the UDL would be 3 times the length. So 3 into 8 is the resultant. So the resultant is 3 into 8 kips. So this is the resultant. And this resultant would be acting at the mid of the UDL. So it would be acting here. So the length is 8 feet. So it would be acting at a distance of 4 feet from this side and at a distance of 4 feet from this side. And it is acting downwards, so minus 3 into 8 minus 10 kips and plus RB. And the algebraic sum of all these vertical forces must be equal to 0. The only unknown is RB, and if you calculate RB from this equation, then it would be 34 kilopounds. Secondly, in order to find out the reaction moment, I am taking the moment, summation of all the moments at point B. So sigma MB is equal to 0. Summation of all moments at point B must be equal to 0. So at this point, this load resultant of UDL is producing moment. So the magnitude is 24 times moment arm. And the moment arm is 3 plus 2 plus 3. So 8 and 4, 12. So minus 12, 24 into 12. Why minus? Again, counterclockwise, I am taking negative. It completely depends upon you, whether you want to take counterclockwise negative or counterclockwise positive. But if you are taking counterclockwise negative, then you have to take clockwise positive. If you are taking counterclockwise positive, then clockwise must be negative. So I am taking counterclockwise as negative, so minus 24 times 12. Again here, this is producing the moment at point B, and that moment is counterclockwise, so minus 10 times the moment arm, and the moment arm is 5. So minus 10 times 5. Look at this. Now this is also a moment, and this moment is actually clockwise, so it must be positive. So plus 20. And this moment is also positive, so plus MB, which is the moment at the support which we are required to find. So looking at this equation, the only unknown is MB. So after calculation, MB is 318 kip foot. So now we have already determined the reaction force and the reaction moment at the support. So we have to move to the next step. The next step is actually to the section method, which we have learned in the last lectures. We have to develop the equations for the shear force and bending moment throughout the beam. But for that, you have to take sections. If we look at our problem, so we have already calculated the reaction forces. The load at the L section has already been replaced by a load and a couple at point B. Sections, one section would be required for this UDL, so that section would work from here to here. But if we move that section, if you look here, there is nothing. There is change in loading. So that section would not work. So for this portion from here to here, we have to take another section. And this section would work from C to D. But if we come to D, so at D you see a moment and a load. So again, section 2 would not work. So in order to further solve it, we have to, because there is change in loading. So what we have to do? We have to take another section, and that section would work from point D to point B. So meaning that in order to completely solve this problem for the shear force and bending moment diagrams, so we have to take at least 3 sections. So section 1 for the UDL, which would work from A to C. Section 2 for this position from point C to point D, and section 3 for which would work from point B to point B. So let's start. So section 1, and section 1 would work from 0 to 8 feet. So this is section, and I'm taking x in this direction. We are taking x in this direction. This is 0, and we are taking x in this direction. And this x would work from 0 up to 8 feet. So here it is written, section 1 would work from 0 to 8 feet. Shear force. summation, the algebraic summation, what we have learned in the last lecture, shear force is the summation, the algebraic summation of all of the forces on one side of the section. Let's say we are considering the left hand side of the section. So the algebraic summation of all of the forces on the left hand side of the section would give us the shear force. And on the left hand side, the upward forces, the sign convention is the upward forces must be positive and the downward forces must be negative. This is the sign convention which we have already discussed. So this is the section, and this is the portion of the beam on the left hand side of the section. This span here is x, so the resultant of this portion of UDL, which is along x, is 3 is the intensity of the UDL times the length is x. So 3x is the resultant of this UDL, and it would be acting in the middle of this portion x. So it would be x by 2 from this side and x by 2 from this side. So and any other load, there is no other load on the left hand side of the section, only this UDL. It is acting downward, so downward must be negative. So Vx, the general equation that we are writing for this section, Vx is equal to minus, because it is acting in the downward direction, and the magnitude is 3x. So this is the general equation for this section. Now what is V naught? V naught means the shear force at x is equal to 0. Here at this point x is equal to 0. So when x is equal to 0, as you could look at this equation, when I put x is equal to 0, 3 multiplied by 0 would be 0. So V naught is equal to 0. V8 means the shear force at a length of 8 feet at this point, that is at point C. So here instead of x, we have to put 8. So V8 is equal to minus 3 times 8, which is minus 24 tips. Next, we have to develop the equation for the bending moment. So at this section, we have to find out the bending moment, and the definition of the bending moment: summation of all of the moments, the algebraic summation of all of the moments on one side of the section. And here we are considering the left hand side of the section. So on the left hand side of the section, counterclockwise, the sign convention is counterclockwise negative, clockwise positive. So if you look here, this load at this section, it is producing counterclockwise moment. So minus, the force is 3x, and the moment arm is x by 2. So 3x times x by 2. So this is the general equation for the bending moment for section 1. Let's find the bending moment here, where x is equal to 0. If you put x is equal to 0 here, bending moment at point 0 and 0 must be equal to 0. And the bending moment at 8 feet, here just instead of x, we have to put 8. So putting the 8 here instead of x, so M8 is equal to minus 3, 8 by 2, and after calculation, it is minus 96 kilo pounds feet. So we have already calculated the important values for shear force and bending moment for section 1. Next, we have to consider the section 2. So I'm taking section 2, and the beam on the left hand side of this section has been redrawn there again. You could see it, section 2, and this section would work from point C to point D. It would work from 8 feet to 11 feet. So section 2, and it would work from 8 feet to 11 feet. And the general equation, algebraic summation of all of the forces on one side of the section. Here you could see that only UDL is acting, and the resultant of this UDL is 8 times 3, which is 24 kips, and it is acting at the middle of this 8 feet here. So 4 feet from that side. And x, again, we are taking the x from here. And x is from here, but this x would work from C to D. So algebraic summation of all of the forces, we have only one force UDL, and the resultant of which it is acting in the downward direction. Downward force in the left hand side must be taken minus, it is negative, so minus, and its resultant is 24. So Vx is equal to 24 tips. Here you could see that it is 24 is equal to x raised to power 0, because here it is 1. So we could write down x raised to power 0, which is actually 1. So this is a 0-degree equation. This is a 1-degree equation. The power of this is 1. Here we have x, but that the x power of that x is 0. So we have 0-degree equation here. So instead of that x, which is already 1, if we plug 8, instead of x we put 8 in order to find out the shear force at 8 feet. So V8 would be minus 24 tips. V11, if we plug 11 for x, which is already 1, so V11 is also minus 24 tips. Equation, generic equation for bending moment at this section, and the algebraic sum of all of the moments on the left hand side of the section. Clockwise positive, counterclockwise negative. So this resultant is producing a counterclockwise moment at this section. So the magnitude of the force is 24 kips, and the moment arm, this is x, and this is 4. So x minus 4 is the moment arm. This is the moment arm, x minus 4. So it is counterclockwise, so minus the force magnitude 24, the moment arm x minus 4. So the generic equation for bending moment minus 24 x minus 4. M8, M8. So instead of x, we have to plug 8. So it would be minus 24, 8 minus 4. And after calculation, we would get M8, the bending moment at this length, that is point C, is equal to minus 96. Chip, the same value. You must get the same value. And M11, bending moment at the length of 11 feet. That is at point B. So M11 is equal to, instead of x, we have to put 11. So minus 24, 11 minus 4 is equal to, and after calculation, minus 168. Next, we have to take the third section. This is the third section, and the beam has been redrawn on the left hand side of this section. Section 3, it will work from 11 feet to 16 feet. It will work from point D to point B, from 11 feet to 16 feet. And again, we have to take the x from here, from this end of the beam. So here x is 0. We have to take x from that end, and it would be up to this section. But this section itself would work only from point D to point B. That is from 11 feet to 16 feet. Because for the this side, for this length of the beam, we have already done the calculations in section 1 and section 2. So again, we have to write the general equation for the shear force. The definition is again the same: the algebraic sum of all of the forces on one side of the section, the algebraic forces, the sum of the algebraic forces on the sum of all of the algebraic forces on left hand side of the section, downward negative, upward positive. So UDL is here, minus 24 kips is the resultant, so minus 24. Here we have the concentrated load at point B, so minus 10. So Vx here is minus 34 kips. V11, again here we have x raised to power 0. We have 0 degree equation. So instead of x, if we put 11, so V11 is equal to same minus 34 kips, and instead of X, if we plug 16 in order to find out the shear force at point B, we would have V16 is equal to minus 34 kips. The equation for the bending moment, the summation of all of the moments on the left hand side of the section, counterclockwise negative, clockwise positive. This the resultant of the UDL is producing counterclockwise about this section. So minus 24, and the moment arm here, this is 40. So the moment arm is x minus 4. This total is x. From this x is p minus 4. So the moment arm for this load is x minus 4. So minus 24 times x minus 4. And then what we have? Then we have this um, uh, moment, and it is clockwise, so plus 20, plus 20. And then we have this load, this load here, and this load is also producing a moment, so plus 10. Here you are not seeing that, but there is plus 10 times, and it is producing sorry, minus 10, because it is producing counterclockwise moment. So minus 10 times the moment arm. And how much is this moment arm? This total is x, and this is 11. So x minus 11. So x minus 10, x minus 11 is the complete equation for the bending moment for section 3. It is some terms are missing, so you have to write those by yourself. So in order to find M11, instead of x, you have to just put 11, and then you have to calculate. After calculation, it is minus 168 hip force. This is the bending moment at 11 feet. And in order to find out the bending moment at 16 feet, instead of x, we have to put 16. And after calculation, we would get minus 318 feet. Some quantities are missing, so first you have to complete this generic equation, and then you have to plug the values. You will get these values, the same values which you are seeing here. So after all these calculations, next we have to draw the shear force and bending moment diagram. So step 3, we have to draw the shear force and bending moment diagram. So we have this beam. What you have to do, you have to extend these lines. You have to extend these vertical lines. So, and also one line you have to pass to point C, and also you have to pass one line to point B. So all important points you have to pass the vertical line as you could see. And then you have to draw a horizontal line which would represent the center of the beam. And here x is 0, and here x is 11 feet. So this line in this direction represents the dimension x of the beam. Shear force diagram, section 1, as we already calculated, V0 is 0. So V0 is 0. So 0. And V8 is minus 24. So V8 is minus 24. Minus 24 would be below this line. So let's say this is minus 24. So minus 24 fixed. And if you look at the general equation of the shear force, it is 1 degree. So the plot of this 1 degree equation would be a linear line. So just join these 2 points by a linear line, 1 degree line. So this line is 1 degree. This is 1 degree line. Next, using section 2, V8 is minus 24 kips. So we are here, minus 24. And V11 is minus 24 kips. So again here at 11 feet, minus 24. And if we look at the equation, 0 degree, 0 degree, and 0 degree line, the plot of 0 degree line would be horizontal line. So just join these 2 points by horizontal line. So it's a 0 degree curve. So it's a 0 degree curve. Next, we have to use section 3. According to section 3, V11 is minus 34 kips. So with section 3 here at 11 feet minus 34, here we have at a point of minus 24. So we have to move 10 kips down. So this is the shear force at 11 feet. And V16 minus 34. So here same minus 34. So at 16 feet, this is the shear force. And if we look at the generic equation, 0 degree, and 0 degree line would be horizontal line. So join these two points by horizontal line. So initially you have to 0, shear force 0, shear force minus 24, and if when we look at the equation, is 1 degree, so linear line. Then minus 24, minus 24, and the equation tells us that the shear force is 0 degree, so horizontal line. Then we move down minus 34 and minus 34 here, and if you look at the equation, it's 0 degree, so horizontal line. So this is actually the shear force diagram. And if you look at the shear force diagram, it is a negative shear. It's a negative shear. All of the shear force is below the reference line. If it was above the reference line, then you would have a positive shear force. Next, we have to plot the bending moment diagram. So all the values have been already calculated. Bending moment at point 0. Again, I have to draw a horizontal line which would represent the axis of the beam. Here x is 0 and here x is 16, and we are taking x in this direction. So bending moment m0, 0. So 0. M8 minus 96. So it would be down below this line. So minus, let's say this is minus 96 kilofeet. And if you look at the equation 2 degree, you could see 2 here. So 2 degree equation and 2 degree plot would be a curve. It would be a curve. So just draw a curve. So this is 1 degree. Shear force diagram is 1 degree. Remember that the bending moment diagram would be 1 degree more than the shear force diagram. If this is 1 degree, then the shear force diagram must be equal to 2 degrees. So the shear force diagram, you could see that the bending moment diagram is 2 degree. Shear force diagram 1 degree, that is 2 degree. Next, utilizing section 2, M8 minus 96. So we are here, minus 96. M11 minus 168. So it is minus 96. So 168 would be below, further down. That would be further down. Let's say it is this point. And if we look at the general equation, 1. So the general equation of bending moment here is 1 degree. And 1 degree would be a linear line. So join these 2 points by a linear line. So this line is 1 degree. 1 degree. And if we look at the shear force diagram at this position, 0 degree. As I told you that the bending moment diagram would be always 1 degree more than the shear force diagram. So 0 degree, 1 degree. Next, M11. M11 is minus this point. It is minus 168. It would be not minus 168. It is typo here. It could be 148 if you calculate 148. 148. So minus 148, and from here minus 148 would be here. So we would move here to minus 148, and then from minus 148 and 16, depending moment at this point is minus 130. So, and if you look at the equation, 1 degree equation. So join these 2 points by a linear line. So again, this line is 1 degree line. And if you look at the shear force diagram for this portion of the beam, it is 0 degree. So the bending moment would be 1 degree more than the bending moment curve or line would be 1 degree more than the shear force curve or line. So if we look at the bending moment diagram, it is below the reference line. So meaning that the bending moment at all these sections is negative, 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 negative. The bending moment is negative. So bending moment is negative, and if we draw the elastic curve, that is the deflection curve of the beam. So looking at this load, uh, uh, so we can easily see that the bending moment on this curve, this beam would be curve like this. So it is concave down. Concave down is negative bending. So it is concave down. That concave down is because here we have the negative bending moment. Let's go back and correct that equation. Okay, so I'm going back and I'm correcting that equation. Okay, so mx minus 24 and x minus 4 plus 20 minus 10 minus 10 times x x minus 8 8 and 3 11 minus 11 that minus 11. Okay. So this is the geometric equation. This data were missing, so I have just rewritten here. So M11, so instead of x we have now 11. So if you plug 11 for x, x minus 11, this term will be gone. So at the end we have minus 24, 11 minus 4 plus 20. I think it is 148. So do that, 148. And here M16, so x, you have to plug x is equal to 16 here, 16 here. And after calculation, you would get minus 318 kips. Various correct. This is not correct, so you have to recalculate and you would get the same value. It is minus 318 kips. We are all and next we have to. Okay, next we have to solve for the bending stresses. So step 4, use beam flexure formula to determine the normal stretching beam. So we have already discussed this beam flexure formula. We discussed that in beam normal stresses are produced, um, compressive and tensile stresses are produced. As you could see that the beam is bending like this. So on the top we would have compressive stresses, and at the bottom we would have at the top we have tensile stresses, whereas at the bottom we would have compressive stresses, and there would be no stress at the neutral axis. And if the beam is of rectangular cross section, then I is equal to the second moment of area. I is equal to B H cube by 12, where B is the width of the beam, H is the height of the beam. And the flexure formula is the stress is equal to M, which is the bending moment, times Y. Y is the distance from the neutral axis in the upward direction and also in the downward direction. And I is the second moment of the cross section area of the beam, which is given here. And Y is plus minus H by 2. So we have to find, also we could modify this equation. We could rewrite this equation as sigma is equal to magnitude of the bending moment at that section, I by y. I'm bringing this y down. So this I by y is actually known as, is replaced by s, where s is the section modulus of the beam. So normally in tables, the section modulus of the beams are given. So either the section modulus value would be given, or if it is not given, then using this analytical model, you have to find out the second moment of area I, dh cubed by 12. If the value of I is given in the form of table, then you could use those values. But if it is not given, then you have to calculate I using this analytical model. So normally the bending moment would be maximum at the outer layer on the compressor side and also on the tensile side. So you have to use y is equal to h by 2. But here we are eliminating y here, so we will be using the value of s, section modulus. So from appendix C in the book, for a W10 into 112 rolled steel shaped beam, the section modulus S is 126 inch cube. So that value is given. Question problem was we have to find out the bending stress just at the left of point D and on the right of point D. So if you look here, just at the left side of point D, the value of bending moment is minus 168 kip, whereas just at the right of point D, the value is 148 kip. So to the left of point D, maximum bending stress. So magnitude, why we have taken magnitude? So we know that the on the, because if the bending is like this, so here on the upper side compressive stress would be there, whereas on the upper side the tensile stress would be there, and below the neutral axis on the lower side we would have compressive stress. But the stress would be maximum at the top layer and at the bottom layer. So the value would be same, only the sign would be different. Plus for the tensile and negative for the compressive. So we are just taking the magnitude so that we only calculate the stress, maximum stress at that section. So sigma m is equal to m modulus by s. So sigma maximum at the left hand side of point P, value is 168 kip. The section modulus is in inches, so we have to change this feet into inches. So changing this into inches, so we are multiplying with 12. 12 is for changing feet into inches. And then after calculation, sigma maximum just at the left would be equal to 16 KSI, kilopound per square inch. And just at the right hand side, sigma m modulus of m by section modulus sigma maximum just at the right hand side is equal to value is the magnitude of this value is minus here, but when we take the magnitude, so plus, so 148 into converting this feet into inches because the section modulus is an inch cube. So multiplying with so it would be in inches, and then after calculation, the maximum stress would be 14 KSI. So what does that mean? That at this section, at point D, the stress at this point would be minus 16 to be minus 16 KSI. However, here it would be plus 16 KSI. Here again, just at the right hand side of this point D, the stress value here would be plus 14 KSI. However, at the beneath layers here, we would have compressive stress, which would be minus 14 KSI. So it must be clear, but generally the maximum stress at these sections just at the right and just at the left, the maximum value would be 16 or 14. Plus minus, you could easily visualize where it could be plus, where it could be minus, where it could be tensile, where it could be compressive. With this, I'm finishing the lecture. Hopefully, everything would be clear to you. Thank you.